A very warm greetings to all the participants here for this webinar. Good morning to one and all present over here. I am more than grateful to stand here and welcome you all on lecture series online webinar on an overview of AI, its component, system and application organized by E-Infochip and Aero Electronics and IESA Gujarat chapter. On behalf of the organizations, I would like to welcome you all and inform you that the webinar will completely enlighten us, your pertaining to AI, all the vital aspects regarding the topic will be conveyed to all. I kindly welcome our today expert, Mr. Sujeeth. Sujeeth is a VP of Engineering at Zentry Lab, a global leader in AI-driven solution. Sujeeth has more than 2 decades of experience in vision and signal processing. In recent times, he headed the R&D division at the AI semiconductor company. He is a passionate AI explorer whose mission to provide cost-effective leading-edge computer vision and NLP solution to customers from domain as diverse as healthcare, fintech, and semiconductor. Sujeeth is an alumnus of IIT Guwahati. So without further ado, let's get started and make this an insightful and engaging online webinar and overview of AI, artificial intelligence, its component, system, and application organized by E-Infochip, Aero Electronics, and IESA Gujarat chapter. Sujit sir, over to you.
Yeah. Hi, everybody. Okay. Let me take this opportunity to introduce you to some of the critical concepts here. When it comes to how do you really migrate the neural network models, building embedded vision systems. Okay. So I title this presentation as embedded vision challenges. So what is embedded vision? In generally defined as okay, it's a compact vision system where you may be targeting a very specific applications like kind of surveillance, the biomedical or sports or underwater imaging and all, right, where the camera system and the processing are sitting together on an edge side. Okay, so the scope of embedded vision when it comes to whatnot actually wherever the camera is involved, right? Okay, healthcare, agri sector, or insurance, manufacturing, banking, even automotive. Interestingly, the recent story from this Tesla, right? Okay, they have removed every other sensor and using cameras all the way for the autonomous navigation of a car and all that, right? So even if you take a surveillance or not, just how the needs are growing up there in that space, like brandishing weapon, we want to detect. Okay, now earlier we were using information, visual information as an evidence once the incident happened or the post incident. Now, can we use the visual systems to anticipate or to stop the incidents happening, right? Like no, threatening theft or whatnot, actually wide applications to make the life easier and productive. So in generally, what is the complexity of these edge systems, right? When it comes to the vision specifically, you may have different contexts and different events defined basically, right? What do I mean by context here is a retail store is one of the contexts, and right now construction site is might be another context. In one case, you may want to count the people, or you want to see the behavior of a buyer on the floor. In other case, in other context, on a construction site, let us say that you want to take care of the employees or workers, okay, whether they are really uh, protected there and the required security is provided for them or not, right? When such kind of systems are in general in vision, when it comes to, we have to build this neural network model based on the context and the events that you wanted to. So you need a model libraries be pre-built, and they should be customized for the different contexts and events. So most in generally, what you wanted to do in vision, right? Object detection, when human interaction is there, you may be most of the time you'd be talking about the pose estimation and how the human is interacting with the environment around them. And the third thing is the scene parsing actually. Okay. What are its surroundings? Okay. Objects existing in surroundings, how the human is interacting with the surroundings and the fellow humans in that, right? So you need a track of both moving and non-moving objects here. And then you may like to describe each of these objects or the humans maybe through attributes, and then you'll mine all this information for the event detection. Now let us take an example. A theft is happening in a camera shop or something like that. Okay, the standard way of the theft happen in electronic stores in generally where the cameras are sold, right? The people, this is information collected over web actually. So the people lift the cameras from the rack and they go it and drop by a trash bin. Once the trash bin is disposed, they go and collect it from the trash bin, the cameras actually. So here the thing is right. Okay, now here one of the object detection is the camera. The human, what he's doing with that an object, where he is moving to, right? We are tracking this information. The event detector may be saying that okay, a camera is picked by a candidate. The candidate moved towards the trash bin and drop the camera is not placed back, and it is neither billed. Now this is an incident, right? Okay, as it happens, we may have to detect it. So these kind of the surveillance systems, when you really want to build these kind of systems, right? Obviously, we have to do or else run multiple neural network models on edge targets actually. So these are one of the points to remember in. If we want to build a meaningful and sensible systems, we may have to run multiple neural networks on an edge target to detect the events while they happen. Okay, that is the point I wanted to specify through this slide. And next thing is, what are different contexts and events a little bit more. Now the people counting, and I have listed a few of these things here. The people counting in a public event case and molesting at a open spaces, right? Okay, maybe a bus stop or any other places, right? Okay, maybe private spaces where the small gatherings may happen, and the theft detection and the safety at work. Okay, but here the challenge is you will not be building a different hardware for the different applications or anything, right? Okay, when it comes to the camera and hardware, once that is built, that has to be configured for the different contexts and events. Okay, many times maybe on the fly at the time of installation itself, maybe you wanted to specify the context and event and don't download the application onto the device, right? So very diverse set of applications on same hardware. Context and events are very diversified again, right? Okay, so obviously we need a lot of fine tuning on the fly, right? So moving forward, if we want to build such kind of sensible systems, actually, Okay, what we need are well integrated tools. As of now, right? If we see, the general tendency is that okay, once we identify some requirement, okay, we may go and browse on the system level, right? Okay, what I want. So if somebody says that I need an object detector, then go and browse for an object detector. You may be going to the Hugging Faces or Papers with Code or XYZ sites. You may get some model, okay. But the thing is that okay, will that be serving your purpose? What are the other models that you may be required to run simultaneously, right? So whenever a problem is whenever we have a problem at hand, okay, that means context and events and operational conditions are defined for you, okay, then you will have to go through the design phase. You may be architecting a pipeline, okay, and what kind of data that you may be receiving, okay, what kind of neural models that you may have to be using and you may have to use, okay, and how do you will be building your report mechanism. Now there would be three parts I can say when it comes to the architecture, right? One is input handling and the presenting the output is the one part. Second thing is a pipeline. Right now there can be, it's not always neural networks to build a complete pipeline. So there may be like the other vision or else image processing libraries that you may have, algorithms you may have to implement. Now along with additional supports if needed, maybe the speech or else audio additional thing might be added there, right? And the third part is the neural networks part. Yes, obviously neural networks is a more complex thing here. Okay, what we do is we once a solution is proposed, then you'll go researching the models. As a first step, you may be accepting them from the model view, okay, and then you will evaluate it, right? Okay, whether does that fit on my hardware and what kind of changes that I may have to bring in them, right, to suit the given context events and the operational conditions. Then we need some sort of model optimization. I put everything in the model optimization where we select a model and get it ready to be ported on the targeted platform. Whole this process I have kept under the model optimizer. So we may have to do here the resource and context aware model optimization. The knowledge distillation is the one part. Let us say that okay, I pick some object detector is fine, but in my context I don't need an object detector which is learned for detecting now 100 objects simultaneously. But if I pick such kind of thing right now, how do you can really make it a smaller without losing accuracy for one or two objects basically, right, of my interest? That is a first level of really dealing with the models. Maybe through the knowledge distillation, and people may be calling it as a two teacher student model sometimes. And some people might have automated it in selecting their architecture at this phase. Okay, so this is one of the phase. Okay, in every engineer right may have to spend some time on. And the next thing is the pruning, especially most of these neural networks when they are trained, right? Okay, we train them with a little bit freedom, with a major concern on accuracy and convergence rates, right? Once we get it, sometimes, right? Okay, we may have to work backwards in removing the redundancy in the networks. Okay, and we may have to kill certain neurons in the network, and sometimes we would like to kill the synapses in the network, right? And then we calibrate and quantize. Okay, if you really want to put on a fixed point architectures, keeping a power consumption cost in mind, right? Then how do we can quantize these complex models? Okay, is one of the challenges. It all comes under the model optimization activity. And the vision bundler, actually, we named it as internally when we have been working on how do we can automate this pipeline and really put it on the targeted devices. Okay, so when we wanted to build such kind of these things right now, it should help in um, easy to handle the models. Okay, now the candidate has to focus more on building a sophisticated application than tweaking the models, and struggling around there actually getting these models converged actually, right? Enable supporting deep learned models on target platforms with an efficiency. Okay, all these things, right? Okay, now we need some sort of integrated systems like this. Okay, still some of them are made, but they are very custom to their hardwares, right? So we're moving forward. The typical flow followed by most of the people, right? When it comes to the model selection, especially, the people go to open source models. Especially ML and vision community and NLP community are pretty good in sharing the information, unlike earlier. Okay, we have a papers with code kind of repositories or Hugging Faces and many more sources for the models actually. Once we take that model, then the immediate question is, does the model fit my needs is the next question, right? How do we can really decide on, right? Okay, one is an accuracy of the model is the one part, and second thing is a accepted latency. Does this model can really process my data in expected time that can be anticipated through the GFlops required by the model? That means floating point operations needed, right? Okay, per second. Now, and the overall computes actually, how much of how many GFlops itself will also give how many computes you need actually, right? And the data moves is another biggest challenge in neural networks. Actually, it's not computes. Many people are coming up with domain-specific hardware accelerators for deep learning neural networks. We have been seeing them. For training anyway, we are using the GPUs from NVIDIA most of the time. For the inferencing, we have various hardware accelerators available are coming up in the market. And controlling this data moves is also one of the very big challenge here. And it's not just computes. And the peak memory needs when we want to really achieve the required latencies. Okay, if that really fit, that's okay. Sorry. Yeah. And otherwise, the pruning and quantization is one of the very important aspects that one has to focus on. And in most of the scenarios, we see this pruning and quantization is an unavoidable step. Then you can pass it through the cross compiler, ML cross compilers, cross compile the models for a given target. And you also have open source targets like a TVM open source cross compiler like TVM cross compiler and Grope cross compilers and all, even custom cross compilers were provided by the ASIC guys. Okay, and the pre and post processing is one of the part. Those libraries also have to be optimally implemented for a given target. Then you can build it. This is a typical flow. Here, my focus of this presentation is to introduce you more of this pruning and quantization, one of the critical aspects of, right? Okay, deploying the neural networks on fixed point architectures. Okay, first let me take pruning part. Okay, when it comes to the pruning, the pruning can happen at a neuron level, or the pruning can happen at a synapse level. Actually, here I have drawn some network. Here the VGG 16-layer network. Okay, yeah, roughly 16 or 24. Yeah, I did not count it exactly, but anyway, here I have. When such network is given, okay, what kind of pruning is possible in generally with these models, right? Okay, one is decompose the complex 3D filters to the 1D filters. That means at each layer, if you see in this new VGG network, you can see each filter, right? Each neuronal filter is of dimensions 3x3 spatial, and the 64 is the depth. If I really see the first 4 convolution layers after leaving the first layer out. Okay. Now, when such filters are given, right, if I can implement them as a convolution of a 1x1x64, that's a depth filter, one depth filter convolved with a horizontal filter convolved with a vertical filter, right? This is the separable concept we are bringing in, but these filters are not so easy to separate like that. Okay, what kind of challenges are there? We'll be discussing them. And then node level pruning. Okay, suppose if I take a 3D filters in each layer, right? Okay, some of them may be pretty much weaker compared to the others actually. Now, can we really remove the weaker filters is the idea here. And the third one is the synapse level pruning. Suppose if synapses coming in, right? Okay, suppose every 3D filter can be viewed as a rack of 2D filters. The output of each 2D filter, right? All of them are added up to produce an output of as output of a 3D filter. So 2D filters at each same synapse level in all the 3D filters in a given layer are weaker. We can kill them at once actually. That leads to the killing the synapse, right? Coming from the previous layer. We'll look into those details. And weight level pruning and thresholding the weight straight away actually, I want to kill the weights, but that leads to sparsity. But implementing unstructured sparsity on a hardware is not easy. There is no specific hardware dealing with that. Handling unstructured sparsity is a more of a software implementation. Maybe possibly, I don't know actually for the sparse matrix implementation kind of things, whether can something be done on a hardware side specifically, I'm not really sure. Okay, so let's dig into these details a bit more when it comes to the tensor decomposition under the pruning. Okay, now here I have some calculations. Okay, when it comes to the filter pruning, decomposition, it can be done in various ways actually, right? Either I can have a rank 1 approximation by using a depth wise, breadth wise and height wise, right? Otherwise, I can also have both depth and horizontal and the depth and vertical. Now we can decompose them in these tensors in various ways. I'm picking a very specific example which I have worked on a bit intensely. Make a rank 1 approximation of a given 3D filter actually. Suppose if I take a 3x3x64 filter, like I'm taking an input of 64 and producing output synapse of 128 layers, right? That amounts to be always, keeping 73,728 coefficients with me. Suppose if I really convert this H3x3x64 to depth filter convolved with horizontal filter convolved with vertical filter, if I organize it this way, then I'm required to just save, keep only 8,960 coefficients. The percentage gain is 87.85%. Okay, and with the confidence I can say that we don't need 3D filters at all actually, because we have verified it on almost different topologies of various complexities. We verified it on almost 150 plus models of a different problem and different problems. With 100% confidence, I can argue that okay, we don't need 3D filters anywhere at all. This is one of very important observation we made, spending a lot of time on that. Okay, and another thing is that we make always a rank 1 approximation for this filter. Every time it may not be possible. Okay, if you don't want to retrain anything, you can use the CP decomposition. Okay, and you can find out there is some sigma missing in this equation actually. L is equal to 0 to L less than capital L. While converting into PDF, that sigma is gone actually. Okay, fine. There should be a sigma summation there. So I can have a L set of such 1D convolutions, right? Where L can be defined as a rank actually, by using a CP decomposition. They may be using it nonlinear approximations to these things. And can we find out a minimal L here in this equation? We'll define a rank of that. As long as this L is satisfying the condition in this particular case, 8960 into L is less than 73728. The smaller the L, better the advantage. But what we found is, given a network, if there are any 3D filters, replace them with the 1D filters, okay, and retrain the model actually, because even the nonlinear approximation also takes a lot of training. But in this particular case, right, okay, you train the neural network itself replacing these filters. But one thing we had to take care of is don't alter the flow of data basically from input to the output side. As long as that constraint is met, and we have seen that this model is converging equivalently to the original network actually, even it is converging faster than that actually, because the CP decomposed components here are initialized with the approximate rank 1 approximations that we are finding out. So the convergence is also pretty much faster for these kind of things, right? And the second thing is node and synapse level pruning. If you look at this diagram, right, okay, now input I'm getting width and height WH and L is the depth. Okay, now the input can be viewed as L layer 2D data. Okay, W class, H class 1, first layer, W class, H class 1, second layer, and so on. And all these layers are fed to one 3D filter. Here, the 3D filter can be viewed as a stack of 2D filters, right? The output of them, when they are summed up, I may be getting one output layer. All these 2D layers, right? If I take all the blue color combinations from that, they are picking the synapse from the same synapse from the input side. Okay, so now here is the scope for me, right? Okay, either I can kill a complete neuron, all the inputs coming to some sigma there, right? Other, I can kill the complete neuron there. Otherwise, I can kill the synapses at each level. Okay, so that from the input side, that synapse is killed. So the neuron from the previous layer is killed totally. So suppose if a node is killed here, a neuron is killed here, synapses that are passed to the next layer, right? Okay, the 2D filters at the synapse level can be cured actually totally. So this is a node and synapse level pruning. Okay, this will also cut down a lot of computes because not all the filters, when we are training, we may be a little bit worried about the convergence and the accuracies. We may be randomly increasing the depth and breadth of the network when we really wanted to train them up. So once it is giving expected results, now we have to go back and working on these things to make the models more portable. Okay. Now when it comes to, right, okay, if I really wanted to remove either nodes or synapses, in general, this is how we organize it as. Here the first row corresponds to the first neuron. Here I have to, let us say, it is a 3x3 cross some depth here. Okay, here in this case, the example taken, I is the depth. And in the first row, first 9 elements are first 2D filter coefficients. The next 9 elements are second 2D filter. And the last 9 elements are the ith layer coefficients, right? So first row consists of all the coefficients from the first neuron. If I look at this data from column wise, right? Column wise, all the data, right? Okay. These coefficients, right? H002, H22. If I take these 9 columns downwards, okay, all these 2D filters will be taking the same synapse from the input side. Okay. So if I take sum of absolute values of all the coefficients across the rows, right, I'll be getting the filter gain of a 3D filter. So based on the gain of the 3D filter, okay, identify the weaker filters and then remove them. When it comes to column wise sum, but 9 columns has to be added up actually when we go for a column wise sum. And then we can kill the input synapse based on the strength. What I mean by here is, suppose if I have a 10 filters, and out of them, the initial first filter has a gain of, let us say 100. The last filter has a gain of, let us say 10. Okay, almost it is the 10 times lower than that. Okay, that may not be producing you the enough strong synapses to pass further. So kill that particular node. Similarly, in each synapse when coming in, those 2D layers itself are weaker, just remove them. Okay, right? We can work back on thresholds to return weights by defining a strategy based on the savings required. Sometimes, right, okay, when I really wanted to prune the model based on the resources available on the target, let us say that. Okay, no, this is what the memory I have to store. This is what the computes I can do. Given such scenarios, okay, we can play around what coefficients has to be stored or else can be used for compute, right? In such scenarios, you can define a threshold and you can tune the threshold to get the required, to save the computes actually based on the target. Even at a weight level also we can prune them. As I mentioned, is unstructured sparsity. As I see, these unstructured sparse models are implemented optimally by neural magic. Actually, they have implemented a compute engine for x86 missions as of now, because on x86 missions you do not have a much cache problem. In such scenarios, they are implemented optimally. Okay, but let us see. Actually, moving forward, maybe on embedded platforms, if sufficient cache is provided, I guess even the sparse implementation also may become attractive. So through this pruning method, okay, I'm showing you some results, what we have worked on. We have verified it on more than 100, near around 150 models anyway. Just I'm giving you two examples here. If I take a VGG19, the original model, to save that, it takes around 574.7 MB memory actually. That's a floating point model. When I really see that parameters, I have a 1.66 million parameters in the model. And the accuracy of the model is around 71%. These two are classifiers here I have mentioned. So when the open window is given by the Intel, right? Okay, they are able to save it, okay, directly quantizing the model. When they directly quantize it, obviously they can save the memory. Storage needed is 143.67 by the VGG19 open window model. And the parameters are also brought down to 143.66 when it is 8-bit quantized. The accuracy published by the open window is around 68.35. When it comes to the model we have built, actually, we have seen, we are calling it as a neuro engine. The model size is brought down to 2.9 MB. Okay, that is a remarkably very good, right? And the parameters we are using is just 2.8 million against 143.66 million. And the accuracy is not much low. It is 69.45. Most of our models within the deviation range of 1.5%, we are getting back the accuracy. So in our case, the retraining is essential, as we are changing. We are not changing the topology as such, but we are changing the filters and keeping the data flow intact. And the retraining becomes as an essential for us. Okay, we are okay with that because we train the model once and then once it is deployed, you may be required to fine tune based on the field ambience and all. Okay, that is fine. That is a motivation for us to go ahead with this. And restaurant 50, if I take it right, we got a 3.55 million parameters against 25.56 million parameters. You can see the savings here. And also when it comes to restaurant 50, the methods that we have built, right, okay, helped us out to maintain the accuracy around nearly 74%, 73.98, okay, against 76.13, the original model actually. When it comes to open, we know you can see that, okay, it is always better than that. We had to stop the fine tuning at some point to save the time actually when we were working on these things. These are the observed results. So the pruning has a lot of impact, but you have to be very careful. Okay. And next thing is when I go back here, right, the pruning and the node level pruning and that part is done. Now once I'm done with this pruning, I'm going to the quantization. So just to recollect the things discussed, pruning will help us out, reduce the number of weights and computes, and ultimately it will also reduce the data moves needed. Pruning can be achieved by expressing any 3D filters as a convolution of 1D filters, and you can also eliminate weaker nodes, and also you can eliminate weaker synapses. The weaker nodes are defined by the gain of the 3D filters in the model. The weaker synapses are identified by the weaker 2D filters at the same synapse level in a given layer. Okay, right? And also the weight tuning is also at each node level. You can quantize or you can cluster the weights, and various things are possible to do that. Okay. Apart from that, okay, the quantization is another important thing here. Here, just I would like to introduce you, if anybody is not aware of, just I thought of recollecting these concepts. What is a fixed point representation of a floating point numbers is right? Suppose here in a integer representation, first the number of bits given, that is important for us always, right? Here in this particular case, total number of bits I have taken is n is equal to 8. Okay. Now I have to really know how many bits I can use to represent the fractional part of a given real number. or a given random variable, and the integer number of bits, how many bits I can allocate to represent the integer part of a given number. Okay, so we call here this something like if f floating point bits are 5, integer number of bits are 3, and total bits are 8, then it is called in generally a format of Q3.5. Okay, 3 integer number of bits and 5 fractional number of bits. Some people write it as 8.5 also. Then in that case, integer number of bits we should calculate that as n minus of f in that case. Okay, so how do we can compute the value of this fixed point, right? Suppose bit position. Here I've given example B0 to B7 if it is an 8-bit representation. The red color V's indicates that the fractional bit values. Blue color V's indicates the integer bit values. S is for sign. Okay. The weights given red based on the integer I is equal to 3, right? First 3 bits are reserved to represent the integer part. The remaining 5 bits are used to represent the fractional part. This is how the weights, the total value is computed here. Minus 1 to the power of B7 here in this case. If B7 is 1, it goes to minus 1. Then it says it is a negative number. If B7 is 0, minus 1 to the power of 0 goes to 1. Then that represents it as a positive number, right? So when I compute the weights here, I have written some example, right? Okay, suppose in a 8-bit, if I write here 0, 1, 1, 1, right, 8 bits and 1, 0, 0, and the remaining zeros, this positive maximum can be computed for the 8-bit, right? Okay, given a format of 3.5, it is 3.96875, right? And the negative maximum is minus 4 in this case, the way we compute it, right? Yeah, the resolution of the data is, we call it as a 2 power minus 5, that is 0.03125. So anything falling in the range of minus of 0.3125 by 2 to 0.3125 by 2, right? Okay, will picking the mid value of that particular range. Okay, what I mean by is, right, the step value here is 0.03125. So it is something like a mid-rate quantizer kind of in general we. So this is a 2's complement representation of fixed point representation of floating point numbers. Okay, now if any x is given to me, I don't know, I'm not seeing any questions so far. Anybody is asking anything? I'm not really sure. Guys, you can post your questions in case if you have any, because yeah, I'm coming to that, setting the fractional number of bits in that part. This I can go here or minimize. Okay, fine. Yeah, here actually, if random variable x is given, okay, now this r suffix small m, the next value is supposed to be r suffix capital M actually. That's supposed to be. The x is a random variable given, and r small m is minimum value, or bigger m is like the maximum value. Then the peak absolute can be defined as a maximum of absolute of these two values, right? Then when such thing is given, the total number of bits is given is n. Then the integer number of bits can be computed as logarithm base 2 into rp, the peak absolute value. So now I can have a integer number of bits, right? Given total number of bits n, and obviously the fractional number of bits is equal to n minus of I, the integer number of bits. So every time we find out integer number of bits and subtract it from the total number of bits, then you can get the required Q format Qi.f. So any variable is given to you. In generally, you look at the dynamic range. Based on the dynamic range, you will compute. No, here the example is, suppose I have something, a random variable x in the range of -3 to 4. The peak absolute value is 4 here. The total number of bits is given n is equal to 8. Then the integer number of bits by using the same formula here, right? I've got 3 and the fractional number of bits is 5. So the Q format can be like 3.5 for this given random variable. So now Q format is selected, then how do I can convert my real data to a fixed point data and fixed point data to real data, right? There's another thing. So if any real number is given, multiply it with the 2 to the power of the fractional number of bits plus 0.5, a round of error, and round it off, okay? Floor the value, okay? So then you'll be getting a fixed point value. There's not any magic here actually. The resolution is 2 to the power of minus f, a given value, dividing it by the resolution to get the actual integer part. So that turns out to be real into 2 to the power of f, okay? Plus 0.5 is given as I want to round the value to nearest integer. So plus 0.5 and floor it, otherwise you can directly write as a round operation, okay? And if you want to back convert this fixed point data, right? Divide the fixed point value given by the 2 to the power of f. F is here the fractional number of bits, right? So I have XR dash. Okay, then fixed point error is defined as, in generally, absolute of the difference between this x prime r minus of xr. Okay, here this gives you the fixed point error in generally. Okay, these are the very typical approach. Selecting a 2's complement, Q format, and Q format selection, and the Q format, the conversion from real to the Q format, desired Q format, and this is how error is computed. So this is a now challenges in building fixed point CNNs. Okay, now this approach looking simple for us, but what is the problem with the neural networks is the next question, right? But here the problem is these neural networks are too cumbersome, actually too big, right? If I take a one layer, okay, thousands of coefficients, thousands of excitations coming as an input, and the output is fan out to the different layers, right? So when I look at the distribution of these data, okay, they may be taking a very ugly shapes many times actually. The may have a higher magnitude, may be significant, and they may have a many values nearer to the 0 also may be significant. So given these challenges, right, okay, here just have summarized some of the points. Okay, the addressable dynamic ranges are extensive at times. The weights and synapses distribution over each layer in general is far from the uniform distribution. Uniform distribution is a very good distribution to quantize them in a better way, right? Okay, because quantization is all about assigning my symbols to the values, right? Real values, right? When a distribution takes a different shapes, right? Okay, obviously I may be allocating more symbols in an unequal region, so I may be losing the effective resolution in the data, right? So error propagation leads to sensitizing network. Fine tuning may be essential. These are like networks filters connected in tandem. If there is any error introduced in any stage that keeps propagated at some point, okay, they'll lumped up and they'll disturb the system. Okay, the possible solutions, we need a careful quantization strategy, and the mixed precision may be one of the good things, and the block floating point representation also may do well actually. Some of the companies are implementing even a black floating point block in their hardware actually these days, okay, just to address the larger dynamic ranges. Okay, and then in practice there are two main ways to go about quantization. One is post-training quantization and the quantization event training. Okay, these are the terminology introduced by people in recent times, maybe over the last couple of years I see them. Okay, now post-training quantization, when it comes to, right, this is about, right, already I have a train model with me. Just I want to quantize all the weights and as well as the synapses there, right? So the first question is, do you need a low bit representation? If your hardware supports the floating point, if the power doesn't matter to you, okay, fine. Run it as a 32-bit floating point model, doesn't matter, okay, right, as long as that is okay for you. Now you may say that I want to 16-bit support is provided. I want a 16-bit floating point model. Okay, now it's all about, right, data type conversion, I can say here. But 16-bit is more than sufficient for most of the models, at least to the date, I have never encountered any model needed more than 16-bit. Okay, and including transformer-based models or even a spiking neural networks, right? Okay, most of the models I observed, okay, I never saw any model needed more than 16-bit. And suppose if yes, okay, parameters can be quantized to 16 bits and you can pass that. Okay, no. Do we have in a 16-bit floating point or 16-bit fixed point? Both of them does equally good actually. I have to say on a safer side, I have to reserve 1%. Otherwise, I can say 100% models can be covered with the 16-bit representation. Okay. Otherwise, no. Do we have a representative data set? Because when I want to down convert, right? Okay, then I have an issue always, right? Okay, do I have a data? Can I fine tune it? If needed, can I retrain it? Right? Then if no, continue with the floating point format. If you do not have any representative data set, better you don't touch it. Okay. Yes, then limit it to int8 format. It's not 89. It is int8 format actually. There's a correction. And then if yes, parameters and activities are quantized, the model executes with only integer operations. Okay, this is a mostly expected thing these days, and the people are going even beyond 8-bit in certain scenarios. Okay, and until 3 years back, even people were crazy saying that I have a 1-bit model. I don't know actually. And some people were saying, okay, we need a 4-bit model or something like that. Okay, it all depends on what they wanted to do. Basically, no, it is not about whether I can implement every model in 4-bit. Doesn't make any sense, right? And they depend on right what kind of hardware they are supporting. And a 8-bit architecture, if I go for a 4-bit model, it is a nonsense. Then right, so it all depends, right? Yeah. So going further, and the quantization, that is a post-training quantization, and the quantization aware training is another part, right? Okay, suppose I have selected some Q formats for my data based on the principles that we have learned just before. I have seen the dynamic range. I have selected the Q formats for the data. Okay, and then but I may see a decline in the accuracy, right? When it comes to the classifiers, right? I may be seeing at a confusion matrix and say that this is the decline in my accuracy, right? Based on that, right? A forward path I can run in a suppose weights and bias are given, right? And quantize them and pass synapses through them, quantize synapses through them, right? And dequantize them, right? Okay, you will be doing it back and forth. In the forward path, you will be running in a quantized fashion. Backward updation part, you will be running it in a floating point space. So you'll be doing it recursively. Still you achieve your model accuracy. This is called actually quantization aware training in generally. And don't train a model directly in a quantized space. I've seen some of the people making such attempts actually, but that takes a pretty longer time to converge actually. Maybe multiple times than converging the model in a floating point. Even a small model to get converged actually took almost in a quantized space where it was converging in few hours for me in a floating point space. It was taking almost days together to converge in a fixed point space in a small model. So till here, okay, this quantization, you have a different tools provided by different people. If you say TensorFlow guys, Google, they have different tools implemented as a part of TensorFlow Lite. Even in PyTorch, also you have a fixed point FP, fixed point Python tools are there, and OpenVINO, they have their own tool set. But in our case, actually, we have come up with our own set of algorithms to do it efficiently, and we have compared open source implementations and as well as custom implementations by these guys. Our approach is giving definitely a very better results, and it is a little bit complex, but it's a one-time approach. So we felt that okay, it is fine. Okay, then our approach is actually first consider the validation data set to quantize the models. Okay, suppose if any given neural network is given to you, okay, do you have okay validation data set? That is the first question. If you don't have a validation data set, in any case, okay, you cannot go for the quantization. I can say if you do the blind quantization, there is nothing guaranteed actually. Even you can cross verify what accuracy that you can really achieve through that, right? Okay. Next, define each layer input and weights, effective minimum and effective maximum. These are one of the things actually. What we found out here is, and as third point also, let me finish that cluster the validation data based and the model sensitivity to give data. Define a set of inputs the model must be evaluated against. Here the question is, our first focus was okay, when we really quantize these models, okay, we wanted to find out how sensitivity is to the data basically given a model when I represent in the floating point space itself. So we tried to condition the distributions of each layer and as well as the synapses. What we did here is we found out the distribution of the weights of each layer, and we found out the distribution of the synapses at each output layer. From the distribution, right, we can easily measure the spread of these distributions. Okay, if they are much nearer to the Gaussian is okay, but if the tail length is higher, how significant the tail length is the question for us. Okay, we had to find out. Cutting down the tail length, we have defined the effective maximum for this. And similarly, zeroing the values nearer to the 0, then we found out the effective minimum. Okay, so whether it can be represented in 8-bit, if this is effective minimum is given and effective maximum is given, because the dynamic range, whatever is we get through the effective minimum and maximum, should be representable in the 8-bit. If it cannot, then immediately we say that out, it cannot be quantized simply. Okay, now we have to scale down the data, model weights and everything, and then we have to redo the stuff here actually. So now we found, and when doing this process, right, if we have a more input data to be considered, right, this process takes sometimes even a weeks together actually. Okay, it was a big worry, right? So then what we had to do, can we really select the inputs which are effective in this particular scenario? There may be, right, okay, I may find out hardly 10% of this validation data set may be useful in penalizing the quantization process. The remaining data may simply pass. We are not interested in such cases. Okay, so how do we can identify and pick them is a big challenge here, right? Again, now we have defined for each input we computed max and minimum at each layer output. Okay, then we defined a vector based on the deviation from the effective maximum and effective minimum. And this, as this strength is very minimal, based on that, okay, we have pruned the list and then we have clustered them, and we had to pick cluster centers is a one, and as well as the points falling away from the cluster center basically for each. So we were able to identify if when it comes to the classification, out of a 50,000 plus validation data set provided by the ImageNet data challenge, we were able to pick hardly 200 samples out of all of them. So we were able to speed up this process basically. So once I get this right, okay, inputs are shortlisted. Now effective minimum, effective maximum, if doesn't fit the 8-bit, okay, then what we can do is the question, right? Now we were scaling down the weights basically, okay, by the factor, and passing these scaling factors forward in the network. Suppose if I scale down the weights by a factor A in some layer L, okay, now the next layer, if it is K, we are passing the scale factor to the K layer because these are the convolutions done in sequence, right? So I can pass the scalar values, move forward, but I have to add this as a gain in the next layer. So I have to keep repeating it till the last layer. Most of the time it is getting adjusted somewhere in between actually. As we move towards the right, actually output side, okay, the weights are generally, the scale factors are generally getting absorbed into the model. So in some cases, okay, if the effective minimum is zeroed, right, okay, some values higher than that when I scale down this, then fine tuning or else retraining may become essential. But this fine tuning or retraining won't take days together like training a model completely. We can close this hardly in a couple of hours. With that, your quantized model would be ready. So from the Gentry side, this is one of the very critical expertise that we have in quantizing and putting the models. Okay, we can also have our own automated tool built actually, which we are calling that as a model cleaver. Okay, If anyone wants, we are providing it as a service. We are not trying to do the business on the tools actually. I'm planning to release that under open source category if anyone wants to use that. Okay, so that's about this presentation. Okay, uh, and this is what I wanted to introduce you guys. The pruning and quantization and the importance of it and how do we can look at it. Okay, yeah. Any questions? I'm open to answer you. Yeah, I see. Yeah, could you please share my any application example how input would look like before and after synapse removal? I do not understand this question. Could you please share any application example how input would look like? Input would be looking same, right? If you are asking about the model, actually. Which one? The question is about the use case. Like, what is your how does no, no, he's asking, could you please share any application example how input would look like before and after synapse removal? No, there is no change in that actually. If you're asking me about output, most of these networks are like classifiers, detectors, or segmentation networks, right? So here the target is that there is no change in the output. Even if that is there, right? Okay, 1% or less than 1.5 percentage doesn't matter in building application by using those networks. Okay. Moving to the next question. How to set fractional number of bits f is equal to 5? Here use 16 layer. Is it fixed or we can change? What is effect of change in layer on performance? So the fractional number of bits are set based on reserving the bits for the integers, as I mentioned. Logarithm base 2 of the 2 into effective peak value, right? Then you can compute the fractional number of bits. What is effect of change in layer on performance? Now there is the impact would be minimal actually when we really prune and quantize these models. The target is to not to lose accuracy. Losing an accuracy if you do pruning, it is again useless actually, right? Sometimes you may like to compromise on accuracy to make the model fit actually. Let us say that, okay, if a model is performing 70% accuracy, let us say that. If I sample the input thrice and make my decision, I may be able to build a reliable system. If such thing is possible, okay, I may be able to like to do the multiple observations of the same data and take decision. And but would like to make my model as simpler as possible. That means cutting down 3% accuracy. If I reduce the complexity by 80%, that is a preferable thing for me, right? So it all depends, right? How do you know how do you design your system and all? Where do you want to use them? Who validates AI tools platform where developers are working? AI tools and platforms, just there is some community like ML Perf is another one community where the people in generally publish comparable results on hardware and as well as the software tools. And they also BDTI, these guys actually organize these validation committees and all. They are no. Otherwise, you can also look at the Embedded Vision conference, these things for the comparison. You may have to find out. These are the things I know, but you may have to. You may be able to find out some more. I don't know. Okay. Yeah, that's all. how to validate data. How to validate data is what data here is the question. If it's image data or is both a big and small question for me. Uh, yeah, that depends on right what kind of data that if it is a classification data is a different scenario, and if it is unstructured or structured is one of the decision making point. Let us say that if it is structured data, what is no you may be defining metrics in defining right. Okay, if it is image data, still I can have a blurriness or the crispiness or different no the brightness, the exposure. These factors I may be defining them in qualifying the data, right? And also maybe I can subsample the data and train a model and see that, okay, what kind of accuracies are getting. Again, I can subsample the data and validate it. I may be repeatedly doing it in a small amount of data, right? Okay. If I do the multiple subsamplings and training a small network, and that way also I can define the quality of the data. I don't know actually what kind of data, no, depending on that, okay, we can take a call. Yeah. Yeah, that's all from my side. Any questions and all, you can definitely post. Can we run quantized model only on CPU or still require GPU? As we no quantized model, even you don't run it on CPU, right? CPU is a floating point processor generally used. Most of the GPUs by NVIDIA or else these guys use the floating point operations. And some of the GPUs from them may be supporting 8-bit format. Actually, again for validation, I can say even embedded category of the GPUs from NVIDIA, most of them are floating point. And fixed point is something companies like earlier we have seen DSPs where we want to implement the speech, audio, and the video codecs and all that, right? A fixed point where the power is of a major concern, right? Even for hardware accelerators in for deep learning models and all, right? Okay. If they have a fixed point implementation, then only we can. Otherwise, we don't need it. It's not CPU or GPU. What kind of architecture that you know? If they have a FPU and you are allowed to use it, given power constraints, that is okay. Otherwise, fixed point. Yep.
Thank you all the participants and Mr. Sujeeth. If you have any questions, you can feel free put your question in a chat box. We'll wait for 1 or 2 minutes. If you don't have any question, then we'll wind up the today's sessions. That is a part one sessions. Tomorrow there will be a part two on overview of AI, its component systems and applications.
Yeah. One question, how can we measure accuracy of model designed? If we validate manually, number of tests would be limited. So any standard process to get accuracy of a model. Yeah, when it comes to the accuracy of a model, right? Okay, this about benchmarking, especially against a standard data set. If it is a classifier, generally what people are doing is comparing against the validation data set provided by the ImageNet data challenge. Every paper, right, what we see is, right, if it is object detector, we publish the results against the COCO data set, right? And like this, for the different problems, we have a reference data set to publish our results against. And how accurate is it is, and how it is solving your real world problems and all, that's up to you, right? How do you productize it? Okay. When it comes to engineering, right, we always look for specific scenarios, right? We won't make really, do we need something which can categorize 2000 classes? Is a question. Do we need something really detected 200 plus objects in a single video? There's something questionable, right? So it all depends on you what you wanted to make. Okay. And it has to work in your operational conditions. Something, let us say that you have built people counting in your lab environment. And if you go and deploy it in a shopping mall, the viewing angle and all matters a lot for you there. Okay, the lot of fine tuning is needed. I cannot say this is giving me 90% accuracy in my lab, should give a 90% accuracy in the field. No, this kind of federated learning is one of the concepts that we may have to look at, how to fine tune these models on the fly. Okay. And is there any tool application that can identify the probable neuron nodes layers that can be pruned without affecting much the performance? Yeah, there are actually, right. Okay, if that depends on what level of pruning you want actually, right? But you will have to, in generally, right, we'll try to remove the weaker neurons and weaker synapses, right? You remove the weaker synapses and then you can validate the model again. Actually, you have to do it in recursively. There is nothing like that. Okay, we can run it in by observing the weights or the synapses strengths. We cannot really say that it can be removed. Sometimes may have some impact. The impact should be minimal. The loss should be recovered with minimal fine tuning. That is in generally the target for the people. Okay. And directly, I don't know, actually, if you push it across, just blindly removing the neurons may have a problem. Yeah. 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 There's some more. Right now, we are observing very buzzing word OpenAI ChatGPT. Kindly share some. Yeah. Yeah. This is right. Okay. When it comes to the ChatGPT, it's a very enhanced version of transformer models, especially, right? Okay. Now you have a lot of data. Okay. And the building a question and answer systems or a huge amounts of data, training over hundreds of accelerators, and implementing RL, reinforcement learning, to correct the question and answers. A lot of manpower as well. Okay, it's almost as far as I read over the news. Okay, right. They took a more than a year, right? It's almost now is we're calling it Chat GPT 3. They have started this effort almost 3.5 years back, actually. From then it had been run. Now the question is, now you are saying we have tried this model with the data until 2021. Okay. Now, how do you can make it now progressively learning is another challenge. So all about right now the thing, now the question is, okay, now it may be changing the way the people are browsing today, right? Okay. Earlier, a programmer wants to copy a code. He had to put some effort in browsing for a code. Now you are getting that instantly before you. That is wonderful, definitely saving the browsing time for the people. But how generative and how creative this model is, I'm not really sure because we try to we tried a couple of examples actually. We asked it to generate a code. Again, we had to put it for the plagiarism. Sometimes, even though we have an exact code available, piece of code available on internet, still it is not showing as a plagiarism for us. Okay, and no, there are many questions yet. We don't know, but as of now, it made the life easy in browsing. For a programmer's perspective, now the general C, C++ or Java application programmers, the life is made more easy. And there are articles, even RTL guys also may be happy with that. Maybe people calling it as a programmers prompting tools for the RTL designers. And also when it comes to DFTs and right in generating the test cases scenarios, there is also some active focus is given on that. When it comes to right, is a scale at which it is implemented. Billions of 800 billion parameters is not a joke. Actually, it's a distributed, but making it realization obviously is an architectural marvel, right? In a distributed fashion. Now I don't know what we can see further, but when it comes to right, let us say that I want to adapt it to a small business. Should I throw all my data into a web into such open category is a question for me, right? How does this chat GPT can secure the private information not going into public and still providing the services? If it can provide is okay, but I have no idea how it can be done. But otherwise, custom solutions with the similar features always may be there. One is a web, a large category, but still I can host my own private model, okay, with a backend supported by the chat GPT, maybe. Yeah. So when it comes to, yes, this is a wonderful proof. And now Google is saying, talking about now we are building a models which are trained progressively. It takes even the current day data and to consume it and they'll reproduce, update it. Maybe I don't know. The Google has to show the difference now. Their first demo was a flop, unfortunately, right? Okay. So no, we have to wait and see. I don't know. First time when the BERT had come, people said that this NLP is killed and everything is done. And now we are seeing, but I see only browsing is made easy and prompting has become better. Okay. The creative talents, I'm not really sure actually. Does it really work like a human brain is always a challenge. I'm not tested it enough, but I have not read any reports on that so far. Regarding their model components and limitations of ChatGPT, the model details, is there no distributed implementation and a multiple GPUs with RL supported training and a lot of human intervention in correcting this data in the beginning years. In last 1 year, how it is trained, I'm not really sure.
Thank you. Thank you all participants. Thank you, Sujeeth, as a wonderful sessions on AI. So thank you all. We'll again meet on tomorrow at the same time at same platform. Thank you. Thank you all.